Okay, so now we're ready to wrap up chapter three. We still have one more important topic to do here, which is measures of association, which I mentioned once before. These are measures that are designed to help us understand both the strength and the direction of the relationship between two different variables. But before we do that, I want to show you something I've put together. People have been asking about the Excel assignments. And so what I think, because we have a fairly short amount of time in this course, is rather than have you do a bunch of individual spreadsheets, what I thought it would be better to do is consolidate a lot of the concepts into a single or small number of spreadsheets. So I've put one together here, which I'll be posting in Blackboard later, which more or less covers all of chapter three. So here's what it looks like. It's called Best Paying Degrees. I will be posting it in a separate folder called Excel Assignments. So you know, they're all in one place. You can see where they are. And so here's what it is. We've got 20 careers or degrees that you could get. And we have two columns of data. We have the starting salary and the mid-career salary. So what I'm going to have you do is, and the instructions are down here at the bottom, by the way, we're going to calculate all these different measures we've been learning. And the instructions are here at the bottom. They want to make it clear to you, for example, that this is a sample, not a population. And then what you're going to do is fill in these calculations for all of these mean through coefficient of variation, except for the covariance and correlation. We haven't done that just yet, but you'll see that those two have to be done on two sets of data. In other words, you'll get a single covariance for the two columns of data, and you'll get a single correlation for the two columns of data. But for all the rest of these, what you're going to do is calculate these measures, the mean, median, mode, quartiles, interquartile range, variance, standard deviation, and all the rest, one for each column. Okay. So again, these from rows 22 through 32, you'll have one answer for each column. And then for these last two, 33 and 34, there'll be a single answer for both columns. So this will be, I think this is a good way to consolidate all the skills that you've learned up to this point in Excel. And if you aren't sure what to do, you can go back and look at the other Excel spreadsheets that we've been working on. And of course, you know that all the solutions, I've been posting them in the appropriate chapter headings. In other words, all the spreadsheets we did in chapter three are in the chapter three folder. The ones we did in chapter two are over there. So you can find them all very quickly and easily. And you can feel free to lean on them. You can go look at them and see how they're set up. The only thing is I just want to make sure, again, that you know that this is sample data. This is one of the things that's easy to overlook. I noticed in exams when I give them in the classroom, it'll say right in the front, this is a sample of data, but sometimes people just don't notice it and they get the wrong one. So this is a sample. So make sure you use the sample formulas and go ahead and fill in all of these, and that will be the next Excel assignment. It'll be due, I'm thinking a week from Sunday, because that would make it, I'll post this information, by the way, that way, because you'll have plenty of time to finish it. So let's look at a calendar of July. So let's see, not this Sunday, that would be too soon. How about Sunday the 20th? I'm going to make a note of that right here, Sunday the 20th. Sounds like a perfect date. Now, the only thing is, since this is not actually part of the mind tap, almost, I mean, I know that it's possible theoretically to set up Brightspace to accept assignments. I'm not so sure if I have the technological know-how to do it. So I'm going to let you know right up front. You can always just simply email it to me. When you're done, just email it to me. If I can figure out how to accept it on Brightspace, I'll let you know. But during the summer, if I realize that I can't do it, you know, the technical support people that would normally be, on their jobs right now might be on vacation. And so it might be more trouble than it's worth to try to get the Brightspace thing set up. So in the meantime, I just want you to be aware that you can always just email it directly to me and that will be fine. All right. Um, but yes, like if I do figure out what you're supposed to do, I'll let you know about that too. All right. Anyway, because I'm not, exactly Mr. High Tech. So, all right. So, but for now, back to the new material, we're going to be looking at these two measures of association, and their names are the covariance and the correlation coefficient. So, the covariance, we'll do this one first. You can see, like with the variance and the standard deviation, there are two separate formulas, and the value of the formula will depend on whether this is a sample or a population. Okay, so remember, n, lowercase n is usually used to represent the size of a sample. Capital N is usually used to represent the population size, just so you can tell them apart. And again, if you recall, the convention is that we use Roman letters for sample measures. S, of course, is a Roman letter. Our entire alphabet is taken from the Roman alphabet, although there are some minor differences from what I understand. And then here we have the Greek letter sigma. Now, keep in mind, we've already used the Greek letter sigma for the population standard deviation. And of course, we've already used S to represent the sample standard deviation. So what gives? Well, for whatever reason, statisticians chose not to create a new letter for these two concepts. Instead, you can tell them apart by the fact that we have two subscripts here. So in other words, SXY means that we're figuring out some kind of relationship between sample X and sample Y. Down here, we're calculating some kind of a relationship between population X and population Y. So the thinking is that that subscript of two letters should be enough to let you know that we're dealing not with sample standard deviations or population standard deviations. Instead, these refer to the covariance. Okay. You do see this sometimes in statistics. Sometimes the same letters or symbols are reused for different purposes. It should be clear from the context which it is. All right. By the way, I forgot to set up some notes here. So I'd like to copy these formulas into here so we have a record of them, not just in the slides. All right. So once again, let me just copy these in here. Now, by the way, when we're done with this section 3B, I'm also going to show you some TI-84 skills that we haven't really talked about just yet, but because, of course, this class is online, you don't really need a calculator, but when you take Stats 2 in the fall, you probably will want to develop as many skills as you can with your TI-84. So before we move on to the next topic, in chapter 4, I would really like to show you some of the keystrokes you would use to come up with these same numbers using the calculator. Okay, it's awfully important to be able to also use the calculators because especially since you're normally not allowed to use a computer during a test. So it's probably a safe bet that you'll need to do both Excel and your calculators. So it takes a while to get used to it, but you'll see it's not too bad. All right, here we go. So these are the two. And now there's other things I'd like to point out to you here. This is again my sample covariance. This is my population covariance. And there's a few ways you can tell. First, like I said before, lowercase n is the sample size. And if you notice in the denominator, this is exactly what we saw with the the sample variance. We divide by n minus one. It's not a coincidence, by the way. So then down here, capital N is the population size. And of course, you notice algebraically, here we have n minus one, here we have n, just like with the variances. Remember, the sample variance we divided by n minus one, and with the population variance we divided by n. It's the same thing. Now, if you look carefully at this formula, you'll notice we have x bar here. We know what that means. That's the mean of sample x. But because we're comparing two different samples, we're going to call them x and y, and this y bar is the mean of the second sample. So actually, you know what that reminds me? As far as the spreadsheet is concerned, when you go to calculate the sample covariance and correlation, I'm going to add one more detail here. I think what we should do here is let the starting salary be X and the mid-career salary be the Y. I just realized I forgot to add that in there. So yeah, this only really matters when you're doing the covariance and the correlation and the graph, okay? Because I'm gonna have you also do what's called a scatter plot, which shows the relationship between the two variables, okay? So that's down here somewhere in the instructions. All right. But for this chapter, I've got a separate example where I will show you how to do this. So by the time we're done with this chapter, you'll have everything you need to know to do this assignment. Okay. All right, here we go. So again, keep in mind, this is the first time we have two separate variables, x and y. So that's why the formulas look this way. There are x's. This is a single element in sample x, and this is a single element in sample y. Now, if you notice, anytime we have two samples like this lined up, we can think of this as x1 and y1, x2 and y2, x3 and y3, all the way down to x20 and y20. Now, it's really important not to get the orders wrong. In other words, the order matters a great deal of these observations when we're calculating the covariance and the correlation. That wasn't true with the other measures. Here it matters. We can't just randomly rearrange them. They have to be in this order because we're comparing them directly to each other. So, like I said, you can think of this as x1 and y1, x2, y2, x3, y3, et cetera, and that's what's going into this formula. And in a nutshell, what you're really trying to do is you're trying to figure out, let me just give you an intuitive feel for what this measure is telling us. The covariance measures the tendency of x and y to either increase at the same time or decrease at the same time. Okay, in other words, so sometimes, oh, and by the way, it can also determine if the two variables tend to move in opposite directions. And it can also determine if the two variables are unrelated to each other. In other words, there's no guarantee that there is any relationship between two variables. So the value that we get out of this measure will help us understand this relationship. Okay. And then, of course, the graph we're going to look at, the scatter plot, will also help us visualize what this relationship is like. Now here, if you notice, with the population version, we've replaced x bar with mu x. The subscript x's there remind us that this is the mean of x, to distinguish it from the mean of y. And of course, in the denominator, we have capital N, which represents the population size. All right, so I think it's time to do some examples. Now, for this one, what they're going to do with this electronic spreadsheet that we had earlier, It's going to make another appearance in this chapter. They've decided to use this as their example of how to calculate covariance and correlation. So that's why it's making another appearance here. You might say, well, listen, we've seen this spreadsheet before. What's going on? Well, we're going to need it again. Okay. So this is that electronics store in San Francisco where they wanted to know if there's a relationship between the number of commercials they're paying for and their sales volume. So it stands to reason that the volume should depend on the number of commercials. So therefore, this is our y variable, and this is our x, because remember, the x is the independent variable, and y is the dependent variable. So this, by writing it this way, we are claiming that the sales depend on the commercials, not the other way around. All right, so now in order to properly calculate these covariances, oh, by the way, they're jumping the gun a little bit here. Let's just focus on the covariance just now. This is the second and related measure that we'll get to in a few minutes. I'd rather show you the calculations first. Okay, now we're going to do this in two different ways. We're going to do it the hard way, which means we're going to do all of the individual steps, and then I'm going to show you how Excel handles this. So you've got, let's come back here to electronics. So we've got X and Y. Let's now calculate Xi minus X bar. Now, I don't think there's any way to reproduce that symbol here, so I'm just going to literally write Xi minus X bar. You know what it means. Then we have Yi minus Y bar. But the thing is, we don't know the values of X bar and Y bar. So let's come down here. And type equals average. Whatever this number is, this is our X bar. Let's do the same thing here. In fact, since it's the same formula, I can just drag this across. And that's 51. Okay, so in other words, the average number of commercials is 3 in this sample, and the average sales volume is 51. Now, for this column, I'm going to take Xi, meaning in this case, this is X1, minus. Now, for this, I need B12, but since it's a constant, I want dollar signs. All right, let's look at that again. Okay. So that's what I need. And now I can just drag it all the way down. Let's do that. Now we do the same thing for Y bar. All right. So here's Y1. And then I need to subtract Y bar, which is right here. That's the 51. C12. And now I've got the difference between the two. In other words, this tells me how far this particular observation is away from the mean. This week I had one less commercial than usual. Here I had two more, two less, the same number all the way down to the bottom. Same thing over here. Since in an average week, I'm getting $51 worth of sales. This week I had one less, 6 more, et cetera, et cetera. Now, if you look at this formula, though, you're going to see that we must, at some point, multiply those two terms together. That's going to be my numerator, okay? So, in fact, I'm going to copy that formula here so we can see it. Just so we can keep an eye on what we're supposed to be doing. So you can see Xi minus X bar, Yi minus Y bar. We're going to multiply these together in this column. And now, of course, I'm going to have to widen this up. This is way too tight. Okay. So look how easy this is. I just literally multiply these two together. And I can drag it down. Great. So now the sum here is what I'm looking for my numerator. 99. So the sample covariance is that number divided by n minus 1. Now, n is 10 in this case. If you notice, there's 10 observations. So it's going to be this number divided by 9, and that's 11. Okay, and that's all you have to do. I mean, it's still a lot of steps, but hopefully you can see exactly what just happened. So, oh, yeah, that's right. So it's 11 because it's 99 over 9. Okay, so you can see they've done the exact same thing down here. They have 99 minus divided by 10 minus 1, which is 11 altogether. Great. Now, you're probably saying, well, that didn't take forever, but man, maybe if there's a quicker way, that would be great. So let's try that. So we're going to go to Excel and see if we can come up with a formula that will quicken this up for us. And so the Excel formula is covariance.s. The .s is there to remind us that this is, in fact, a sample covariance. All right, you got to get that straight. Now, it says array 1, array 2. It doesn't matter which you pick first, X or Y. Just pick them both. And there you go. It's 11. All right, so it's done. All right, and now you understand how to do it in Excel, and you also understand how it's done. Now, because this is a positive number, since the covariance is positive, this indicates that there is a tendency for both variables to rise or fall at the same time. In other words, in weeks in which we have more commercials than usual, there's a tendency to also find larger sales volumes. In weeks when we're below the average number of commercials, we tend to find less sales as a result. But it's a little tricky to interpret this. The covariance has some issues that we need to mention right here. As a measure of association, it does have some drawbacks. Mention that right here. The covariance as a measure of association has two major drawbacks, actually. Number one, there is no upper or lower limit. So that it is difficult to interpret it, or it's difficult to interpret. So in other words, in this case, with a covariance of 11, it is clear that this relationship is what we would call positive, meaning that they tend to go up and down together, but it is difficult to judge or determine how strong this relationship is. And we'll discuss this a little bit more in a couple of minutes, but number two, the covariance is affected by the units in which it is measured. What does that mean? Well, like as an example, if we are analyzing the temperatures in two different cities, the value of the covariance will be different if the temperatures are expressed in Fahrenheit and in Celsius. And that's not good. Okay. In other words, the result will depend on the units in which I'm measuring this. And that makes things a little bit tricky. So to overcome these issues, A closely related measure may be used. It is known as the correlation. You may have heard that word before. It's often used in other applications and other contexts. The correlation, like it's a general all-purpose name for the strength of a relationship. Like if you say, well, there's a high correlation between, for example, temperature and ice cream sales. Well, I think intuitively you understand what that means. When it gets hotter, people buy more ice cream and vice versa. So yeah, you do tend to see that word used in, not necessarily statistics class. You'll read about it in articles you might be reading on the internet or something. And so it is known as the correlation coefficient. Now, luckily for us, it's not difficult to calculate because it's directly related to the correlation, the covariance measure. So let's go look at these formulas and see how they are related to each other. There we go. Now, of course, there's a separate version for samples and populations. In fact, what I'm going to do here, let's see, just to avoid running out of space. I guess we can leave it on this sheet. Just maybe have to move a few things around. I need some more room to show the correlation coefficient here. Um, let's see. Now, the only problem here is I'm going to need to do one more thing. Just add another row here. In order to calculate the correlation, we're going to need the standard deviations of the two samples. Okay, so we know how to do this. STV dot S. Remember that dot S is needed in Excel. Select all of these. Okay, that's approximately 1.49. And then for X, Y rather, I can just drag this across. Okay. So you'll see in a minute why we needed to do that. Okay. So the bottom line here is that the correlation, let's move it over here. And by the way, I'm going to copy these both into this notes so that you can see that there's a formula for both samples and populations. And Greek letters everywhere in the one with populations. So let me just quickly mention here, this is my sample correlation coefficient. And this is my population correlation coefficient. You can tell by the Greek letters, but if you notice too on the top, look at this. This is the sample covariance that we just calculated. That means I need to now divide by the product of the two individual standard deviations. Now, one thing I want to point out here is that for the first time, we have subscripts here, and that's only so we can tell them apart. Okay, we have SX, the sample standard deviation of sample X, and we have the same thing for Y. Subscripts remind ourselves which is which. And then down here, of course, you might not recognize it from before, but that's the population covariance because we didn't use this example. And down here we have the standard deviations. Of populations X and Y. And not only that, but now there's a new Greek letter. You might not have noticed it right here. This is the Greek letter rho. Specifically, it's the uppercase rho. Um, Up here in the Roman alphabet, the corresponding letter is R. Now, if you notice, the formulas are the same, except, and in other words, algebraically, they're identical to each other. Now, you might not think so. Given that the covariances were calculated differently, you might think that these two measures would give us different results, but it turns out that in spite of their different appearances, unlike the covariance, the correlation coefficient will be numerically equal for both samples and populations. So there's Excel doesn't actually have a separate function for sample correlations and population correlations. There's no need for it because they always give us the same result. So when you go in there, don't look for the sample correlation coefficient. It's not there. It's just one function for both. Okay. That seems a little strange, but that's how it works out because there's a little cancellation going on that causes this to happen. But anyway, let's go back here and finish this up. What I needed to do now, in order to come up with the correlation, I take the covariance and divide by the product of the two standard deviations. And now I end up with 0.9304, et cetera. And guess what? I can also do this with Excel by typing equals correl, as it's called, X and Y. And it's the same, of course it is, it has to be. It's the same formula. Okay, so now you know how to calculate the covariance for a sample. For a population, the difference would be dividing by n instead of n-1. And you know how to do it directly with the long approach, and you know how to do it in Excel. Okay, now going forward, you can certainly feel free to always use the Excel version, but still, it's good to know how both of them work. Now, that raises an interesting question. Why is knowing this number more important than this number? How does the 0.93049 give us more information than the 11? That's a very good question. Okay, so that's what we're about to address. So for the electronics example, covariance between commercials and sales volume is 11. The correlation coefficient is approximately 0.93. So the correlation coefficient is not affected by units. In addition, it has an upper and lower bound. Specifically, if you're dealing with the sample correlation coefficient, it has to be somewhere between negative and positive 1. The same thing is true, by the way, for the population version. So in this case, the correlation of 0.93 shows that not only is this a positive relationship, in other words, X and Y both increase and decrease at the same time. I'm sorry, or decrease. But the relationship, and we'll describe this in a minute, what this actually means. The relationship is very strong, which means that in the overwhelming majority of the cases, when X increases, Y nearly always increases And when x decreases, y nearly always increases. Now, it's difficult to visualize this without a graph. So that's what we're building up to here. There's a special type of graph that we can introduce to help us visualize these types of relationships. And that type of graph is known as a scatter plot. We're going to do that in a second in Excel. The scatter plot shows the relationship between two variables. Okay. So let's go back into Excel and create one of our own for these two variables. Select, insert, recommended charts. Pick that one. One on the top is it actually says it right there, scatter. All right. What is this supposed to tell us? Now, the graph looks a little strange because there's so few observations, but in general, what we're trying to look for here is to see if there's any kind of a pattern. So if you introduce a trend line, as it's called, right-click trend line, that trend line has a positive slope. So what it's saying is that they tend to both move in the same direction almost all the time. So with the scatter plot, you're observing each one of these points. For example, this one, I don't know if it's possible to show a label. Let me just see if I can do this. Doesn't seem to want to work. Each one of these points is a single week. In this case, let's see, this is 1 and 30 something. That looks like week 6. Okay. If you notice in week 6, we had one commercial and our sales were $38. And then way up here in the upper right, we have about 5 commercials and, oh, there it is. There's the label, 5,63. Oh, it's even giving us what point it is. What do you know? That's the 5th point. Oh, well, as far as it's concerned, that's the 5th point. All right, 563. So that's that point. Each one of these points is a single observation. So what I'm going to do is show you in general what these graphs can look like and how to interpret the correlation coefficient. So we start with a case where with X and Y, and we have something like what we just saw. Now, by the way, I do want to mention here that here we have data that has to be positive. We can't have any negatives. So all the points will be in the first quadrant, but sometimes if the variables can be negative, points could be scattered all over in all 4 quadrants. Here it just so happens we have all positive data. So let's say we end up with this. So this one is defined as a strong positive relationship correlation coefficient will be close to 1. It's positive and close to 1. But what if we had 2 variables that are positive, but not, the connection isn't quite so strong? We'd know because the points are not quite so close to that scatter, that trend line. So yeah, there's a positive relationship there, but it's not nearly as direct or strong. So we can think of this as a strong, weak relationship. R is positive, but close to 0. Right, like 0.2 or 0.3 or something like that. And then we can have something like this. Where there's just no connection between the two at all. X and Y are independent. R equals 0. This is two variables, like with the store in San Francisco. What if, let's say that X was instead the weather in LA or some ridiculous thing like that. And why is the sales volume at our store in San Francisco? Like over here with the rainfall in LA, and we have sales at our store in San Francisco. Well, clearly they're not related to each other. And that's how you would know it. And then we can move on to the negative cases. Say the points look like this. So the trend line is negative, and but the points are very close to that trend line. So we can think of this as a strong, weak relationship. I'm sorry, what am I saying? Strong negative relationship. Sorry about that. So R is close to -1. Okay. Now I did the same thing here. Sorry about that. Oh my God. This one should have been weak and positive. I'm glad I checked. You're probably confused. That's better. So strong and positive, weak and positive, no relationship at all, strong negative, and then the last case is strong, weak and negative. And again, you see the points are not that close to the line, but they're still a general negative pattern. So we say here that this is a weak negative relationship. So that means R is negative, close to 0. Like, for example, -0.2 or something like that. So those are the cases we're looking for. And so in our example, that 0.93 means we're definitely up here in this area. So that means this is telling the store that those commercials are really generating sales volume. Because almost invariably, when we have more commercials, we have more sales. Now, that doesn't mean they're worth the money, of course. It depends on how much the commercials cost. But at least we know that the customers are responding to the commercials. The more commercials they see, the more likely they are to come into the store. So that's very helpful information to the store. So this is our correlation. Now you can see why this is so much more helpful. With the covariance 11, what does that mean? It's hard to be sure. We can tell that it's positive, but the magnitude doesn't tell us anything. That's really the drawback. So, but on the other hand, we do need the covariance because the correlation is derived from it. So we can't just ignore the covariance. We need it as a starting point to calculate the correlation. So both of these are important. And for some mathematical applications, it turns out there are some things about covariance that are convenient. So it's not like it's completely useless, but for stats, it really is better to look at the correlation coefficients. All right. And when you get into finance class, you'll see some important applications. This helps us understand how well diversified a portfolio of stocks is. And that's a huge deal because it helps us understand how much risk is present in our portfolio. All right. Now, I'm about to show you some TI-84 instructions. We're going to take a bit of a detour into the TI-84. So for that, I've made up a separate example. And that would be right here. We've got two variables that could mean anything. So what you have to do is enter this information into what are called lists. All right, let me just copy this. Into our notes. All right, here we go. Now, this, by the way, you don't really need what we're about to do for this class. You may want to use it down the road, but right now, um, you don't really have to do this. But I think it's a good idea. So we start by entering the data into lists. Now, unfortunately, I can't really show you what I'm doing here because it's hard to see, and plus it's going to be backwards. So, but I can verbally explain to you what we're doing. So we're going to go to stat, hit the find the stat button in the upper left-hand corner, then hit, it's already on edit one. And you'll see a bunch of lists labeled L1, L2, L3, et cetera, et cetera. Now, if there's old information there, you'll have to clear it out. So you have to go up there with your arrow key to the header, not the first row, but the header, and hit clear, enter. That will erase everything. Okay, you have to do it for both columns. If you've already used this before, you probably have old numbers in there. And after you've done it once, you'll always have old information. So clear enter. Now you just literally type the numbers and you hit the arrow key after each one. So you just manually type 0, -2, 3, 5, and 7. After each one, you hit the down arrow key. Now to get to from L1 to L2, move over to with your arrow key and go down and do the same thing. We're going to let L1 be X and L2 be Y in this example. So type in -1, 5, 4, 2, and 1. Now, when you're done, you have to get out of this mode. Or actually, it may not be absolutely necessary. If you were to go to stat, if you hit the stat button, okay, no, very good. All you have to do is hit stat. Now, in the stat, when you hit stat, you've got three options in front of you: edit, calc, and tests. You're going to hit calc, and then you're going to choose one bar stats, enter, and then now what you're about to do is come up with the statistics for L1, list one, which is X. So it already says list L1. If it doesn't say the one you want, you're going to type second followed by the number of the list that you want. We're going to do that in a second anyway. We're going to switch over to list two, and that means hitting second two switches to L2. But for now, let's leave it at L1. And then you're going to scroll down and hit calculate. Okay, so go down with your arrow key, enter, and then you're going to see a bunch of information here. X bars listed. Okay, Then there's SX, which is their sample standard deviation, 6469. All right. And then it's got some quartiles in here. You notice how it has Q1. It may not have everything. Q2 is not listed, it's listed as median. As you remember, the median and the second quartile are the same thing. What else is it giving us? If you notice, it doesn't have a separate entry for the variance because it's understood that you can simply square your standard deviation. And it has max, and that's kind of it. So it's not everything maybe you were hoping for, but it does a pretty good job. So to find the numbers for Y, switch to L2. And so that means going back here, stat, calc, one var stats. All right, so stat, calc, one var stats, which means one variable stats. Okay, great. Enter. List. So you want it to say L2, so you have to type second 2, and then go down to calculate. All right. And then when you do that, you'll get the same stuff. I mean, for this, you'll get X bars 2.2, SX 2.387, Q1 is 0, median is 2, Q3 is 4.5. And that's all we need. Okay. Now, what about the covariance and the correlation? Okay, here's what we have to do now. We're going to go back to stat, calc. But this time, we're going to pick number 2, 2 var stats. Hit enter. Now make sure, now this is really, really, really important. Make sure it knows which is your X list and which is your Y list. So the way we set this thing up, we put X in list 1 and Y in list 2. You must not get these backwards, okay? So remember how to enter those numbers. Second, in this case, if it's not the right one, hit second 1. And for this one, we would hit second 2. If they're already right, well, then you're all set. Go down to calculate. And hit enter. And if you scroll down enough, you'll see, oh, now see, this is unfair. You see what they've done? I didn't realize they were going to do this. Oh, they expect you to do it yourself. So in other words, what you have to do here is look up S. Oh my God. Well, I guess it's not here, is it? Or at least it is. No. Wow, I didn't realize that. They don't seem to have it. I'm sure you could reproduce it from these numbers, but I'm kind of disappointed. I thought it would be here. Okay, so in other words, unless there's something in there that I didn't know about, I guess that means they don't have it here. You know what? That seems very hard for me to believe. Let me just check something. Oh, I didn't see that in there. Hold on. Maybe I just went right past it without realizing it. I swear I did not see that in my list. No, I don't know what they're talking about. Maybe I have an outdated calculator, but I do not see sigma XY in here. No, I don't. Well, I don't know what that's all about, so never mind. I guess we're not going to be able to do this one. There seems to be some question about whether it's in there, but I mean, those are the steps we did, and it's not in mine, that's for sure. I don't get it. This is the first time I've been disappointed in this calculator, let me tell you. It's usually pretty good, but no, it's just not here. All right, well, forget it. You guess for that one, you'll have to use either use it, manually, or else you'll have to use Excel. I'll put a big question mark here. But anyway, so that was it for chapter 3. Now, what's coming up next? Chapter 4 is a very, very different subject. It does not, unfortunately, have any Excel spreadsheets to go along with it. But not all of these topics lend themselves very well to spreadsheets. So um, what we're going to do here is introduce probability theory, which is the foundation of all of statistics. So it's an awfully important chapter, but it's more conceptual than computational. Up to this point, we spent a lot of time doing calculations. Here, that's going to change a little bit. It's more about theoretical relationships, but I think you'll find, though, that it's extremely interesting. So I guess we'll say that for the next session. So next time we will introduce chapter 4. In the meantime, this assignment here that I mentioned earlier, I'll be posting the template in a separate folder so you can find it, and then we'll have it due on Sunday the 20th. Okay, that should be due enough time to get it done. So all right, then I guess that's everything, and I'll see you next time.